morning, everybody. So today we're going to do our lesson of notes, and you probably have them in front of you. You'll see that they're probably a little shorter than the average set. So this is kind of our finishing off set for the unit. So a quick reminder of what's happening otherwise. Next week's kind of a weird week. So we have Halloween on Monday. I don't really have anything structured for Monday, just because I'm kind of figuring it'll be a crazy day with haunted house and whatnot. Tuesday there's no school. Wednesday I would like to do another quiz. Then Thursday would be a day to be able to go over said quiz and make some corrections if there's still things you don't get. But for the most part, the quiz you guys wrote a couple days back, minus adding 2 new formulas, one from yesterday, one from today, it's more or less just the same thing still. So that takes it to Wednesday quiz, Thursday, kind of a day to go over it. Friday would then be another day off again. So we have no school on Tuesday or Friday next week. And then the following week, Monday, then I'd have to do the unit test for this. And I feel like that's probably a pretty reasonable timeline. So, you guys agree, or do you feel like that's not going to work? You okay with that? Okay. In terms of stuff then, I think I screwed up on one of those. Monday we don't have a work day. Monday we're doing a lab, I think it was. I screwed that up, didn't I? Monday we're doing a lab. It's going to be a bit of a different lab than you guys have done in the past. Let me show you right now, actually, because I think I have the time to afford for it today. The lab that we're going to do, we're going to test the forces of gravity, and what I have is a simulator, which apparently is up to date. But that's okay, it'll still work, so we'll skip this. Essentially what it is a quick little Java applet that's been written, and I'll find a way somehow to email this to you guys or to upload it somewhere, because it's a small little file. And all you do really is you change the weight of an object. See how I've got a sliding scale here that changes the weight of object 1, a sliding scale that changes the weight of object 2, and then you can change the distance between them. And you guys will notice that the force that's being measured, as I manipulate any one variable, changes the amount of force. So if I drop down the mass, the amount of gravitational force between the objects is lower. If I make the masses really large, well then there's more gravitational force. If I pull them further apart, there's less force. Put them closer together, more. Does that make sense? What I'm going to have you guys do is we're going to create a graph. And so we're going to test this for multiple different things. We're going to control the mass of, say, one variable, set it to whatever. And then the other variable, we're going to change the mass, record a point, change the mass, record, change the mass, record, change the mass, record, change the mass, record, and plot a graph. Remember what the relationship is as mass increases to what the force of gravity would be? Direct or inverse? Direct, yeah. You should have a linear graph essentially. Then what we'll do is we'll control both masses, so we'll make them, whatever you want to make them, it doesn't matter. And we'll do the same thing with the radius, and we'll change the radius to being a little bit different, a little bit different, a little bit different, a little bit different. And that should cause a reciprocal graph, which some of you guys know this shape, or you guys in grade 11. We're covering it after we finish this unit we're doing on patterns, but it has this sort of shape to it. Whereas the radius goes up, the force of gravity goes down. Does that make sense? It's actually a really simple little lab to do. Obviously, I don't have any sort of apparatus that could actually test the amount of gravity between objects, because that's crazy to imagine we could devise something like that in a high school lab. So, anyways, that's the lab for Monday. It's pretty straightforward, actually. So, for you guys at Livingston, this is why I don't actually need you to be here, because you can really do the lab by yourselves. So we'll just have to find a way for me to get you this applet, because really I have it stored on my computer in one of my files here. It's 2,000 kilobytes. It's not really all that big. It's just slightly bigger than your first quiz, honestly, in terms of size. So, okay, let's do our set of notes here, as I'm getting off topic. Last day we talked about gravity. So gravity is it's one of the 4 fundamental forces. Not that you need to know this at this point in your physics lives, but the 4 fundamental forces are gravity, which, it basically has pulled, to our knowledge, it's pulled the universe kind of together. It's what keeps us tied to Earth. If there wasn't gravity, we could end up floating off into outer space. There wouldn't be an atmosphere for us to breathe. Gravity is pretty vital for life to ensure that we have the conditions we need, right? So that's one force. Another force is the electromagnetic force. So that's anything involving magnets, anything involving like positives and negatives attracting each other. Honestly, that actually is the basis for most of chemistry. I didn't think about this yesterday, but really what makes an ionic compound? A positive cation and a negative anion. If it wasn't for those electrostatic forces keeping stuff together, we would have no ionic compounds. We wouldn't have stuff. Third force is the weak nuclear force, and this would be things like radiation given off from decay. So when you hear of like nuclear power plants that end up melting down or something like that, and they give off, you know what I'm talking about, stuff like that? That's another type of force. We'll actually cover decay and fusion and fission, that sort of stuff at some point. The last one's the one that I don't really know even how to describe all that well. It's the strong nuclear force. I think it makes a little bit of sense as to that there must be some sort of force tying a nucleus together, because all those positive protons in a nucleus, really there's no reason why they should be next to each other. Positives hate other positives, right? They're like enemies. They want to spread out, right? But for some reason a nucleus stays together, which is good, because otherwise all matter would just explode and we'd have no stuff again. So there is something tying it together. We don't actually know what it is. We just call it a strong nuclear force, and that's what physicists are working on nowadays. They've got all these cool theories about things like dark matter and dark energy, and that's kind of cool stuff. But anyways, I digress. I'm getting off topic. We're talking gravity. So what we talked about yesterday a lot of is the idea we need to have universal gravitation. If physics really is going to hold true, it has to be true for the everyday life stuff, for you and me. It has to be true for the infinitesimally small stuff, like atoms and protons and electrons. But it also has to be true for the extraordinary large, like planets and suns and galaxies and solar systems, right? So we know, however, what gravity on Earth is. It's 9.81. And we can calculate that pretty easy just doing experiments. I mean, here's a quick experiment. Drop an object. Its velocity initial is 0. Determine the distance it falls, because you can measure that. Determine the time that it falls, and you should be able to find an acceleration pretty easily. Just doing like, I won't drop this pen again, but right, just drop an object and measure like we do in labs. So we are pretty comfortable in saying that gravity is 9.81. In terms of terminology, that would be empirical or experimental evidence. If I ever use those words, which I think I did in chemistry last year probably, empirical just means something that you can tangibly go out and test. Right? I have tested, I have proven that in a lab, gravity is 981. But now that we've got this universal law of gravitation, we have an ability to improve it theoretically. Maybe here's another way of me describing these two words. If you guys watch the Big Bang Theory, anybody ever watched that show? The two main guys on it are Sheldon and Leonard. Sheldon is a theoretical physicist. If you've ever watched episodes, he does most of his work in front of a whiteboard, and he says, well, this is the way hopefully life does work. Leonard is an experimental physicist. He actually has a lab and goes and designs experiments, trying to then see whether that is actually indeed the way that the world does work. Does that make sense? And they're kind of two sides of the opposite sides of the same coin, if that makes sense. So let's do a little thought experiment. We are now physicists. Let's do some theoretical physicists. We have experimentally done, in theory, in some labs, figured out that gravity can be 981. Let's prove it on paper. So here's how you might do that. We need some formulas. We actually have two. Right? One of the formulas we've learned about for forces is that the F net is equal to ma. Right? The net of all the forces is mass times acceleration. We believe Newton's law is right. Let's say I drop my pen. It's the only thing I have to do. Let's say I drop this pen. What was the only force acting on? Gravity. It was a free body projectile, right? So I could then say that really the force of gravity is equal to mass times acceleration. If it's okay with you guys, I'm just going to put a little g next to the acceleration, though, because really, why do we have this acceleration? It's due to gravity. So then what I could do is I could say, well, what other formulas have I now learned for the force of gravity? Well, yesterday, the universal formula was big G, m1, m2 over r squared. we actually kind of did this yesterday with the whole determining the mass of the Earth. Because this mass right here is the mass of the object being dropped. One of these masses here is the object being dropped, and the other one is the mass of the Earth. You know what I mean? So based on that, we should be able to cancel one of them, and really the mass that's left is the mass of Earth. So what we're left with is a formula that looks like this. The gravitational constant times by the mass of, and rather than saying Earth, just for right now, I'm going to change that and say the mass of the planet that you're on. Because in a second, we're not going to calculate gravity on Earth anymore. We're going to calculate gravity on Mars, the Moon, Jupiter, the Sun, whatever it is you want to work with. Okay. Essentially, we've made a formula where the gravitational constant times by the mass of the planet you're on, divide by the radius of the planet you're on, should give you the acceleration due to gravity on that planet. Does that make sense? And then yesterday we kind of discovered that we have all these constants that are written down for us all on the same sheet of paper even, right? So 6.67 times 10 to the minus 11, there's your gravitational constant. Okay.
I misunderstood what she wanted.
Thanks. Mass of the planet, what was that, 5.97, 10 to the 24? .98, 10 to the 24? 97? 5.97. I'll start writing E, 10 to the 24. And then divide that by the radius of our planet, which is 6.37. Yeah. I haven't done this in a while. Yeah. You guys have the sheet in front of you? Somebody confirm this for me. You with me hanging. Yeah. 6.37 to the 6. And then don't forget this bottom number needs to get squared. This would give us the acceleration due to gravity. But it's the acceleration due to gravity on Earth. Right? Hopefully you can kind of see where I'm going with this. Eventually we're going to now calculate the acceleration due to gravity on the Moon, on Mars. Right? So now you just need your calculator. But what should this hopefully turn out to be? Hopefully 9.81. 6.67 E negative 11 times 5.97 E 24 divided by bracket 6.37 E 6 and square today. Do you guys feel like that using E is actually going to be a little bit of a time saver? Hey, look, it's 9.81. Right. So we've now confirmed gravity on Earth from an experimental point of view is 9.81, because I can just do an experiment, drop an object, see how long it takes, do some kinematics, ta-da, we got our acceleration, right? But theoretically, we didn't do any experiment here, we just used a whole bunch of known constants, and we found the same thing. So this is basically the point of my lesson. We're now going to calculate what gravity is on any body of whatever. Does that make sense? So a couple of notational things here. Your data booklet now is not going to use A-G, kind of like that. They're going to use G, and sometimes they might put like some lines around it, depending on the convention there. Let's do a data sheet. I'm trying to remember what I did here. Yeah, there's one there. Well, they did actually use A-G on the constant, didn't they? Okay. So you may see some different things here. If you've got the sheet that talks about constants, you might see that they did A small g equals 9.81 with the, you guys see that one on your constant sheet? I mean, we kind of knew this one already. You may see this as just g with a couple of lines around it. So I'll talk about that in a second, but this essentially is your gravity. Sound good? Cool, moving on. Okay, gravity is actually considered to be a field, okay? Maybe I should talk about those lines right now. You know those two lines that were sitting on opposite sides of that G that I was kind of pointing out there? Let's talk about that now. Grade 11s, sorry, we're doing this in again about 2 weeks. Grade 12s, we did this last year. What do those lines mean? Yeah, it's called an absolute value. Yeah. Essentially, the idea is that if it's a negative number, it makes it positive, and if it was a positive number, it stays positive. It's called absolute value. We'll do it in a little bit. The idea here being that there really is no up or down direction anymore. Think of the Earth as a three-dimensional object hurtling around space. Which way is up? Which way is down? Let's say we even tried to define this up here as being up and this up here as being down. Do you see the problem here? For us, being on, like, say, this side of the planet, gravity is pulling us, sure, that way, let's call it negative. But at the exact same time, there is someone down here in, I don't know, what's down here, Argentina, where their gravity is actually pulling them kind of the other way, if that makes sense. They're really up and down. Sometimes it doesn't really make as much sense because regardless of where you are on the planet, it's all going in, I guess. But even then, that's not fair because the way gravity works is that the planet pulls you in, but in a way, you're actually also pulling on the planet, which means maybe it's better to say this is a double-sided arrow as well. Does that make sense? So that's one of the reasons why we put the absolute values around it, because we really don't want to consider positive or negative in general. Like, we will as we solve a question, but it's really not fair to say that it's always negative or always positive, because as a big picture sort of thing, it's kind of pulling from here, it pulls that way, from here it pulls that way, from here it pulls that way, from here it pulls that way. You know what I'm saying? So it's kind of directionally challenged. That's what I'm going for here. So what we use is we use the term to call it, we call it a field. A field is a 3D region of influence, where either you get attracted or repelled. And we're going to start talking about these in gravity and then eventually with magnets and electrics as well, where direction is less relevant. It still matters, okay? But it only matters once we actually get into the problem and say, okay, now which way is left, right, up, and down. Does that make sense? Here's an example of Earth's magnetic field. You guys probably know a little about this, right? Like, we call this side of the Earth north and this side south. And if you had a compass is actually a small little magnet, and it points towards the North Pole and away from the South Pole. Right? But if I was right here and I was pointing north, this guy right here is also pointing north technically. But I mean, look at the way I've drawn it. I mean, if we did consider this to be in, like, say, 3 dimensions, one is kind of going up and to the right, and the other one's going up and to the left. That's technically a different direction, yet they're both going north. So hence the idea of a field. That makes sense? So we'll talk more about them as we get to other units. Long story short, we can actually make a new formula now. This is known as a gravitational field strength. Essentially, what we've done is we've taken the mass times acceleration formula, combined it with the big formula of g m1 m2 over r squared, and we just canceled away one of the masses, which is kind of what I did on the first example. And so here's a brand new equation. If you want to find a gravitational field strength, which essentially is an acceleration, just so you guys know. The field strength is essentially the acceleration value. Right? And then this is the formula. Take big G times by the mass of it, the planet you're on, essentially, and divide by the radius of the planet you're on. But the reason we call it a field strength is that I can't really guarantee which direction it's going. I mean, it's getting pulled in, I guess, if you want to use in as your direction. Does that make sense? So let's do a couple of calculations. Here are some planets in our solar system. Or Pluto got left off the list. Really, we could calculate any planet's gravity now, right? So hypothetically, you're NASA, and NASA wants to send a rover to Mars. Right? And they want to say, well, how much do we need to compensate for the fact that Mars is maybe a bigger planet, maybe there's more gravity? Right? How do we deal with that? Well, we just calculate its gravitational field strength. So its gravitational field strength is big G, the mass of, say, Mars, over the radius squared of Mars. I'm not actually going to calculate every single planet here. I'll just do it once if that's okay with you guys. So if we did Mars, 6.67 times 10 to the minus 11 we've determined that Mars has a mass of 6.42 times 10 to the 23. And it has a radius of
any students in grade 7 who are needing retake? Any students in grade 7 needing retake, please come to the hangar, to the weight room for your pictures.
You guys feel like this is something that you could pretty easily repeat so long as I gave you the information? Or if I give you a gravitational field strength, you could then go backwards and calculate either a mass or a radius. So it's a pretty straightforward little formula. Let me know when you guys get an answer. Go ahead. 3.7? Okay. Okay, I was wrong. Apparently Mars has less gravity than Earth. I don't know, I thought it had more. Now that I look at those numbers though, Mars is actually a little bit smaller in mass, isn't it? Earth is to the 24, Mars is to the 23. So that's probably the biggest reason why there's a discrepancy, is that Mars is a little bit smaller in mass. It's also smaller in radius, but I'm guessing the mass probably makes more of a difference though. Easy enough? Okay. What did you say it was again? 3.41? Thanks. Okay, so just one more thought here. The units are meters per second squared, just like an acceleration is. But we use the description field to describe the idea that really that pulls in all directions. North, south, east, west, however you want to try to describe it, it's pulling inwards. I had to actually do a description. I don't know why I left so much room there. I guess we could do more examples, but I get the impression. Probably okay on this? Okay, so based on that, let's add to this then. This is almost, these examples are silly almost. But what would your weight be if you were standing on Mars then? Now I want to make sure that we use the words properly. Weight is different than mass. You, if you weigh 110 kilograms, always, I used the wrong word, didn't I? If you mass 110 kilograms, that is your mass. Right? Weight is really mass times the effect of gravity. But there's less gravity on Mars. So hypothetically, if you were to take a bathroom scale from Earth, take it on a spaceship to Mars, for whatever reason, and you decided to weigh yourself on Mars, you would weigh less, right? I could dunk a basketball on Mars, I'm guessing, right? If gravity is only a third of what it is here, I could jump pretty high, I bet. Right? So how much weight do you have? Well, I mean, this formula is still the same. The force of gravity, which is really how you're calculating weight, is still mass times your gravitational field strength. In the past, I've always called G gravity, but I need to change my vocabulary now. G is actually not gravity, it's gravitational field strength, dependent on the planet you're on. We're just almost always on Earth. So you could then do 110 kilograms times by 3.70, blah, 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 meters per second squared. Okay, that's your answer. You weigh less. Normally it would be 110 by 9.81. Help me out. 110 by 3.70.
107.
Perfect. All right, whereas normally, I just want to go off to the side, on Earth, it would be 110 by 9.81, which would be, well, it's going to be like about 1,000, I'm guessing. Close enough. All right, so you guys can see that you have less weight. That makes sense? Okay. One last example. This is also very silly and strange. I can only think of one time where this is really relevant. But your weight would actually change if you were in motion. Let me give you an example on Earth first before we deal with Mars. Hello. Anybody want breakfast? Okay, thanks guys. imagine that you were in an elevator. You guys have hopefully been in an elevator at some point in your life before, right? When you go up in an elevator, can you kind of feel yourself getting pulled into the floor a little bit? Right? Whereas when you go down in an elevator, it's almost like you separate from the floor just a little bit and you become a little bit more weightless. Does that make sense? If you had an elevator that was really free falling downwards fast, you might actually experience weightlessness to a degree, where the bottom of the floor is falling beneath you almost as fast as you're falling yourself. Right? Whereas if the elevator is going up, it's like it compresses you. Does that make sense? Well, this would mean that you would have more apparent weight or less apparent weight if you were actually already in motion. Does that make sense? So hypothetically, one of you one day becomes a NASA astronaut, you go to Mars, you now weigh less on Mars, because it's Mars, but now you're on a spaceship that needs to accelerate away from the surface of Mars. Because of the fact that the spaceship itself is accelerating, you and the spaceship are kind of getting compressed into it, you would kind of have more weight. If that makes sense. Let me show you the calculations. Here is U. I'll just use a box. And normally, the way U would work is that you have a certain force of gravity that goes downwards, right? What prevents you from just falling indefinitely for forever? What opposes gravity? Normal force, right? Really, it's your normal force. That's what the scale measures. Does that make sense? If you're standing on a scale, you know how you push down on the scale? Well, the scale pushes back up on you, and when the scale pushes back up on you, that's how it registers what your mass is. It's not actually measuring your force, it's actually measuring the force of the scale pushing you back up. Right? And as much as it pushes you back up, there's like a little spring inside, and the spring depends on how much it needs to push back at you, tells you where your weight happens to be, right? Or your mass happens to be. Right? So essentially, when you're weighing yourself, you're actually determining the normal force. Now, what would happen if you were actually traveling in an upwards direction? Well, if we were to draw a free body diagram, it would look something like this. Your normal force minus gravity would be equal to mass times acceleration. Makes sense? That I'm kind of skipping a step here, but the net of all of your forces would be normal is kind of pushing you up. Gravity's pulling you back down, but you're in a rocket, and the rocket is accelerating upwards. You're going to get pushed into the floor. Does that make sense? It would be maybe similar to if you were in a vehicle and all of a sudden the person steps on the gas and you go, whoa, right? Because what's happening is you're not actually going backwards, but you're getting like forced into the seat behind you because the seat behind you is coming towards you so quickly, if that makes sense. Right. So since the scale is really measuring the normal force, if I want to calculate that amount.
For all Block 1 teachers, please have your attendance done ASAP. All Block 1 teachers, please have your attendance done ASAP.
Everybody here? Room is okay. Back to this. Okay, sorry, I'm going a little faster than I want to here. Does this make sense? The normal force is really what the scale is measuring because it's how much a scale would push back on you with. Right? That minus gravity would normally equal 0, right? Because normally you're not traveling when you're on a scale. Normally you're just standing there and there's no acceleration. So your normal force is equal to gravity. But what happens if you were in motion and you're on a rocket ship accelerating? Well, then to find your normal force, you'd actually have to add gravity onto the other side, which makes sense because you're now going to feel a little bit heavier on the scale because the scale is getting pushed into you just a little bit more. You know what I'm saying here? So to calculate this, then we would take your mass, which was 110. We would times by the acceleration of the rocket ship, which was 20.5. And then we would add how much force of gravity you would have, which we just did on the previous slide, because we're doing the force of gravity again on Mars. So that would have been your 110 times by Mars's force of gravity, which was the 3.70. So this is normally what you would weigh, but we have to add a little extra because the scale is getting forced into you. You know what I'm talking about here? Does that make sense? I have a hard time trying to visualize, like to manipulate it. Right? I don't know. What can I do here? This is our rocket ship. This is our astronaut. Normally, if you just sit here like that, imagine this there, right? This guy is getting pulled downwards, but the ship is pushing him upwards, right? What happens if the ship is moving too, right? What ends up happening is that this ship is pushing on him almost from the bottom side as well, right? Normally he pushes down, the ship pushes up, right? But now he's pushing down, and the ship is pushing up, but he's also pushing up more, because otherwise you just stay there, right? The ship has to push up even more to get it into the air, so he's actually going to feel more weight. If it went the other way, you might actually feel like weightless. So essentially, to solve a question like this, it's not hard. You just have to wrap your mind around it. Either you have to add on the mass acceleration, or possibly subtract a mass acceleration. Right? If you should theoretically feel heavier, add some more. If you should feel lighter and weightless, because you're like dropping, subtract. Does that make sense? It's almost kind of a ridiculous thing to suggest, because, I mean, I know physics is starting to explore now, it's supposed to be universal, right? This should happen anywhere, but when do we need to bring a bathroom scale to Mars and figure out how heavy you apparently weigh, right? Like, it is kind of silly. So, you guys able to get an answer for that? $2,600. You guys get the same thing? Okay. One thought before I forget about it here. You know how you guys have a possibility to do a Mythbusters project? The reason why I threw it in for this unit is because you may want to consider doing a movie like, say, The Martian, Gravity, Armageddon. You've seen any of these movies here where they travel to outer space and there's less gravity. Deep Impact. You've seen any of those sorts of movies? You may want to see whether you can try to calculate how much gravitational field strength there would be on the asteroid. Have you ever seen Armageddon? It's got like Bruce Willis, Ben Affleck. We need to have a movie class one day. Anyways, the basic premise of the movie is that there's an asteroid that's going to travel towards Earth and will destroy Earth. They fly an oil drilling crew up in a spaceship to land on the surface of the asteroid, to drill into the middle of the asteroid, to then drop a nuclear warhead into the middle of it, causing it to explode, causing the asteroid to split into pieces. Totally ridiculous. But anyways, you can do some cool stuff with the movie if you wanted to, if you know it, because you could try to calculate how much gravitational field strength there would be on that asteroid, because there is some gravity on the asteroid. There was way less. They actually had problems in the movie with bouncing off the asteroid and never being able to get back to it. One guy got lost in outer space, actually. So, anyways, as I was thinking about that, if you wanted to do a Mythbusters project on, like, The Martian, have you ever seen The Martian? Yeah. Okay. You know how at the end of the movie, Matt Damon needs to try to find a way to, like, launch himself high enough up to make it to the spaceship that's trying to capture him, kind of thing there? You can check the plausibility of that scene, and you could try to calculate how much gravitational... I mean, we actually know how much gravity there should be on Mars. Right? So, anyways, it might be a fun thing to try. Or you could omit the thing, too. So. Okay. This makes sense? Okay. That was my last slide, right? Yeah, we're done. Okay. So quick recap then. From the very, very beginning. This unit, honestly, it actually has just as many lessons as the first unit. Right? Like, if you actually look back, we did 7 lessons in kinematics and 7 in dynamics, but I would gather that this probably feels, in general, easier than kinematics. You feel like it's better? And I wouldn't say that the topic is actually easier. It's just that you're more conditioned now to what it's going to look like. Like, relatively speaking, when you started physics, I had an analogy in my mind. It would be like a train is whizzing by, and you're standing still. And as you watch the train whiz by, you're like, oh my goodness, this thing's moving fast, right? But now you guys are no longer standing still. Now you're in a vehicle traveling next to it. And the train is still moving pretty fast, but you're also moving. So relative to the train, it's maybe not so bad anymore. But it really hasn't slowed down. I don't know if that makes sense. Hopefully that's the case for you. So what we learned this unit then. That's good. Okay, here's what we talked about then, the main concepts. We did unit Nota forces. Right? To push or a pull. That was kind of our first day, just talking in general how forces work. Then we spent 3 days talking about Newton's laws. So I've beat them to death. You should hopefully know them. Inertia, mass times acceleration, equal opposite reactions. The fifth lesson was kind of one of the most important ones. It involved gravity, or it involved friction. And it probably is the most challenging of all the questions you get, because I need you to be able to solve a question that involves friction, a downhill force, a gravity, possibly tension in a rope, and like any subset of those variables, solve them on like say an angled incline. Right? So there may be a downhill force, or not. There may be tension in a rope, or not. There may be an applied force. You know what I'm saying here? So you should know how to solve most of those things, especially on an inclined plane. You may also need to break things up into the x and y dimensions, where if I push this way and my buddy pushes this way, then which way will it actually travel? The question I gave you on your last quiz was about guys trying to push the car out of a snowden. That's a pretty typical question. And then the more recent stuff we've then covered is, can you calculate gravity the big formula way? Big G m1 m2 over r squared. So if I give you planetary data, massive stuff, or even if I give you an infinitesimally small stuff, like say the mass of a proton, the mass of an electron, could you do the same thing with that? Because there's gravity between them. And then today's topic is, can you actually calculate the acceleration due to gravity on a different planet? Because, this would be really cruel, but I can make you do all the kinematic stuff and all of the dynamic stuff, but rather than using 9.81, we could have to use a different number. Does that make sense? Like I could ask you, on Earth, if I throw this pen, how far will it travel? And then I can make you redo the exact same question and say, on Mars, if I threw this pen, how far would it travel? All the numbers would be the same except for the acceleration. Does that make sense? So, questions? In terms of stuff then, we have 2 labs to do, one which we finished, one which we'll do next week. Most of you guys have finished the first assignment, right? So start working on the second assignment. The magic school bus, I should mention. I've made an answer key for it. I'm going to have you guys mark that yourselves. Here, let me show you my answer key. Just quickly. You're not going to like this, actually. You probably won't like this. Okay, what I've done is I've made an answer key here, and I've actually typed it out in red is what I've got here. And I've underlined some like key sections where I'm hoping you have something written similar to me. But I'm going to leave this up to you guys. I've done this before with other classes, and this is why they don't like it. I'm not going to tell you how many marks each question is out of. You could make the first question out of 1 mark, the second question out of 3 marks, the next one out of 4, but the person next to you could make it out of whatever. Because honestly, I don't care. I just want you guys to learn. So I want you to compare your answers to mine, and if you feel like your answer is more or less what I'm saying there, then you determine how many marks you think it should be worth, and mark it out of that. And if you feel like, oh, I should have written about that, you're right, oh, I see what you wrote there, you know, then maybe you say, I'm going to give myself 1 out of 2, or 2 out of 3, or 3 out of 4. I really don't care, guys. Okay? And so at the end of the day, well, here's what I need from you guys. I need you to mark it, and you might mark it out of 21, and you might mark it out of 57, and you might mark it out of 5. I want to mark out of 100 then. Does that make sense? Just so that everybody's in the same playing field. Because really, what I more want you to just do is think. Right? The grade doesn't. You guys know this what we marked right now. Like, I don't care as much about the marks. So use your own judgment. If you really are struggling and are like, I don't know whether I should get 2 or 3 on this one, then you can ask me over if you want. But honestly, I trust your opinions. And I think this is worth doing once in a while because I think you guys need to do more self-marking. In the maths and sciences, it's kind of easy for me to throw you the answer key and say mark it yourself, but I think there's room for that in the subjective interpretation fields too. So, does that make sense? So, I will trust your judgment. I really will. So, be fair. I'm not saying that you have to have the stuff that I've underlined and bolded, but when I went through, that was kind of the key thoughts. Like, for example, a definition of a force. Hopefully you have the words pushes and pull. You probably don't maybe you have it written exactly like I do. right? But hopefully you have some of these key concepts. So, does that make sense? Okay. For you guys over there, I will email this to you as well, and I'll throw it in your Dropbox folders. You guys have any questions? Okay. I'm also going to start moving the answer keys over to the sidewall. I bought some sticky stuff to put on the walls, so hopefully now they're not like way up high. They're more reasonable.
Yeah, I could totally not.
Yeah. Okay. You guys are good? Okay. You have like, I don't know, 10 minutes left-ish. Let me pause the recording though.